István,
Um,
thanks for chatting.
Thanks for having me.
All right, first question. Why do they call it SolidWorks when it never works?
I can't comment on that. It's like this question makes me very uncomfortable.
Okay. The solution to that problem for you was go build a better thing?
I can't go down on that rabbit hole, unfortunately.
Okay. Understood. Well, on that rabbit hole, let's go into the technical side of it. What is a CAD kernel?
Ooh. How much time we have?
Yeah,
So
as much as we need, because
Yeah, okay.
I want to demystify it.
Okay, so a CAD kernel is basically that software component that implements the geometry, the math under every CAD system. And if you talk about MCAD, mechanical CAD, that's typically a boundary representation kernel. So the mathematical concept and the algorithms and the data structures that that CAD kernels implement are typically BREP or boundary representation algorithms and data structures. That's the foundation. That's basically the mathematical foundation of every CAD, CAM, and CAE system when it comes to working with geometry.
Okay, when you say the boundary representation, what is that, and why is the CAD kernel responsible for that?
Yeah, so BREP or boundary representation is this mathematical concept that describes shapes with like 3D shapes with their boundaries. For example, a cube that has 4 sides is that has 6 sides or 6 faces. It's represented like every single face is under the hood. It's represented as an infinite plane, and on that infinite plane you have 4 edges that lay on that plane, trimming out that rectangular face from that infinite plane. And once you have 6 of these, you can stitch them together along their edges. And if you did a good job with the construction of the geometry and with the construction of the BREP data structures, then you end up with a cube. And that cube is represented with its boundaries. So the faces represent the boundaries of that cube. It's a very like natural concept in a way, because like it's interesting that this concept of faces and edges is a really natural way of interacting with bodies and working with geometry, and it also has really important machining consequences. So when you're machining a part, you actually want to have those parametric curves and surfaces accessible in the geometry. That's one of the advantages of BREP. And the other advantage of BREPs is that BREP as a mathematical concept, it basically became a protocol between industrial applications. So if you can read and write BREP data, then you are quite compatible with all the other tools.
But why? So first of all, why do you need to represent the data, period, in something like a boundary representation?
Why do I need to represent it?
Well, so for instance, in computer graphics, we've had
Yeah.
shapes for decades.
Yeah.
Right? And we had them in 2 dimensions and then eventually 3.
Yeah.
So why didn't we just use whatever the graphics industry?
Why are we not using meshes or any other representation?
Like I think what's confusing is, why is it sufficient for video games but not for machining parts?
Yeah, I think it really comes down to these 2 things. That first of all, the workflow, like a CAD workflow, a modeling workflow, is based on interacting with faces and edges, and no other representation has faces and edges in a way as BREP has it. So the structure, basically the geometric structure, the topology and the geometry that a boundary representation body provides is a really, really nice and easy way to create shapes for manufacturing. That's one of the reasons, and you don't really have the same workflow with meshes, so like triangle sets, or you don't really have a same workflow or similar workflow with sub-D or any of those other geometry representations, simply because BREPs let you select an edge and apply a round on it, or they let you select a face and apply like a an offset operation or an
like
extrusion.
manipulate it.
Yeah, exactly. So it's the way BREPs work. That's just a really, really, really natural and easy way to create shapes for manufacturing. And also, it's not just that it's easy to create shapes with BREPs for manufacturing, but also this property that basically BREP holds parametric curve and surface information that makes it really, really easy to process it. Not easy, but it makes much easier to process it for manufacturing with a CAM system, for example, than like other representations.
I see. So,
and last but not least, it's really the precision, right? If you have like a mesh body, basically you're approximating the geometry with a bunch of triangles, and you will also have like it's always an approximation. Like unless you have like a really, really dense network of triangles, those tolerances are not going to be acceptable for manufacturing. It's just like the tolerances are too big. With BREPs, you are working with parametric curves, which are like a much better way to approximate geometry accurately with floating point numbers that computers work with.
So, why have we? Firstly, has the world standardized to BREPs, and if so, why?
Yeah, I mean, yes, pretty much it did. You can say that BREPs became the protocol between applications in the last 50 years. The first BREPs were invented in the 1970s. It was pioneered by a few mathematicians in the UK in the 1970s, and then the first BREP kernels that we are still using today were built in the 1980s. And of course, they went through like pretty significant development since the 1980s, but conceptually, BREP has not changed since the 1970s or 1980s. And in the 1980s, it was like a really like a natural decision or a really obvious decision to just go with BREPs because it had unique advantages for machining and for the computer architectures that we had in the 1980s. BREPs made a lot of sense. And because of that, every single CAD vendor started building BREP-based CAD systems. And what we are using today as CAD, like all of those tools are BREP-based. There are 5 BREP kernels in the world that are mainstream. Siemens Parasolid, Granite by PTC, Shape Manager by Autodesk, and you have ASYS and CGM by Dassault.
How many are actually licensable, though?
I mean, if you go to the vendors, like everybody will tell you that, oh, we would license the kernel if there is an opportunity. Like realistically, I think it's mostly Parasolid and ASYS. I think Dassault is also licensing CGM. I never really met a company that is using CGM directly as a
even their own SolidWorks doesn't run it.
No. Like SolidWorks. So this is like a famous one of the more famous conflicts in our industry that SolidWorks was built on Parasolid. In the 1990s, John Herstick's company licensed Parasolid from Shape Data. That was an independent company at the time, and then SolidWorks got acquired by Dassault in 1997, I think, and Shape Data got acquired by Siemens or Unigraphics at the time, which obviously creates like a pretty rough situation between the two companies. And SolidWorks famously tried to replace Parasolid for a long time, but they never really succeeded. And that's not because they don't have great software engineers, or not because they're not good at like writing software. It's simply because a geometric kernel, is actually almost like a programming language itself. So like replacing it means almost like rewriting an application from scratch. And that is not even the biggest problem. The biggest problem is that you can't really guarantee backward compatibility if you replace the kernel, because basically you would need, if you're switching from kernel A to kernel B and you still want to be compatible with the earlier versions of your software, basically the two kernels would have to be compatible on the bug-to-bug level, which basically means that you need like the exact same implementation for every algorithm, which is like not possible.
What do you mean by bug to bug?
So even the bugs would have to be the same in the two kernels.
Or you would have to account for both sets of bugs, so double the work.
Yeah, like I mean, it's like what I'm trying to say with this is that you literally need like the level of compatibility has to be like 1-to-1. Like you need the exact same implementation for every single algorithm, including the bugs and including all the like everything has to be the same.
So this is actually a really interesting part of Shaper 3D's story that isn't talked about much, which is that you are one of the few CAD companies that actually switched kernels.
Oh, we did, but it was very early, and it was a little bit of a different situation. So Shaper at the time was relatively small. We had a much smaller user base, so that obviously made it easier. And the other advantage we had at that time is that Shaper was a direct modeling tool, so we did not have a feature tree, we did not have parametric history, which makes it much easier to switch kernels. Because most of the backward compatibility issues arise when you want to like rebuild a feature tree basically from scratch, and then the level of compatibility that you need is even higher. If you are just transferring the BREP data without a feature tree between the two systems, then yes, it's much easier to switch kernels. Even then, it's quite hard, and you have to rewrite like a lot of code, but it's easier.
So I don't want to beat a dead horse on this, but I just want to get a really clear answer about what a BREP is and what the kernel is and why it's so important. Mm-hmm. So the BREP, so the kernel is what creates the geometry that everything in the CAD application uses for measuring distances, defining geometry, et cetera.
Everything that is related to creating, measuring, querying geometry, all of that is the kernel. It's like, but it's just that, like basic operations, like create a line between these 2 points, or extrude this profile in this direction, or create a loft between these profiles. Like these are the foundational like building blocks of creating geometry.
So, what is so difficult about them? Why is the math behind it so difficult? Why is making it performant really difficult? Why aren't there more alternatives? Right now there's only one open source really.
Wow. Yeah. Geez. Well, that's a lot of questions. So let's maybe start with why it's so difficult and what's the biggest problem with it. So the biggest problem with creating a BREP kernel is that BREP as a mathematical concept, it's just fundamentally flawed. There are a few issues with BREPs. The biggest problem, one of the biggest problems with BREPs is that a BREP body is basically it's two data structures. One is the geometry, so what is the shape of the entities that you have in that BREP body, and the other is the topology. So what is connected with what, basically. And
when you say connected, you mean the surfaces or the bodies?
So where do I have an edge that connects two faces, for example? Like which faces are connected with which faces?
Okay, so not to interrupt, but I just want to make this clear. You're saying the two things being held here are the actual geometry itself and then the interfaces or the intersections between them.
Yeah, not just the interfaces, but really so the intersection, like an intersection could be like, it's still, it could be a geometry, like what is the shape of the intersection, but really like basically these facts about the shape is like these two vertices or these 2 points where these two edges meet are the same points. That's or these two edges or these two these faces are actually meeting here at this edge. So that the connectivity information basically between the different elements. That's the topology. So you have these two data structures. You have the geometry that describes the shape of every entity, and then you have the topology, which describes what is connected with what. Now, I think intuitively, everybody feels that what is the shape of the entities and what is connected with what. These are not independent from each other, right? Like quite obviously, these are somehow intertwined, right? But that's not how BREP handles it. And then you have these two separate data structures that, in a way, these are like basically describing something like shared properties between geometry and topology, but yet they are completely separate. And then you have to make sure that these two data structures are consistent. And that's one of the hardest problems in building a BREP engine. This is called like double bookkeeping between topology and geometry. And the problem with this is that even theoretically, it's not possible to solve this problem robustly. Because just imagine this situation that, like obviously because we are working with floating point numbers, we have to work with tolerances, right? So two vertices are equal if they are quite close to each other, like they're closer than a very tiny epsilon value to each other. Then if you have two vertices, then it's relatively easy to determine if those vertices they belong to the same vertex or not, or 2 points belong to the same vertex or not. What if you have three and pairwise they are closer to each other than epsilon, but not all of them are closer to each other than epsilon? So what happens then? What's the solution for that?
Do you just fuzz the number?
It's like,
do you like just draw volume around it?
Yeah, that's one of the solutions. Yeah, you can increase the tolerances, right? And then you have like that's one way to resolve this.
Sorry, real quick, just to be clear, when you say these tolerances, this is inherently a flaw in floating point arithmetic in that you can't have exact numbers. You're always going to have some.
I would say that this is an inherent flaw in how BREPs think about topology and resolving these geometric inconsistencies.
Because part of that is that you have to define each surface or each vertex or edge in a floating point number, and then those can be plus or minus whatever the tolerance on a floating point 32 number is.
Yeah. So let's say that we increase the tolerance when we run into a case like that. What happens if you have four?
You just picked one up accidentally.
Once you have four, you can further increase the tolerance. But what happens if you have like 1,000 in a row, and the distance between the two furthest points is like 1 meter, but your tolerance is like 5 micron? Are you going to increase the tolerance of that vertex to like 1 meter, and then suddenly you messed up your entire model, or what are you going to do with it? So now this is a relatively artificial example, but these are exactly the type of problems that you run into when you are building a BREP kernel. It's like there are like a lot of these issues that don't really have like a really good answer, and not because we don't have smart enough mathematicians to figure this out, but simply because conceptually it's broken. So that's one issue. Like this topology geometry inconsistencies, topology geometry bookkeeping. This is one of the hardest problems. The other super hard problem about building a BREP kernel is that there isn't like an easy and unified way of implementing most BREP algorithms, especially when it comes to local operations. So like fillets, shells, face offsets, pretty much everything that just locally modifies the geometry. So not Booleans. Booleans are still super hard, but in a different way. But when it comes to local operations that just locally change the geometry, those are brutally hard. Why is that? It's because there is like BREP doesn't really provide you an elegant way to define these operations. So let's say that you want to fillet an edge, and next to that edge that you are filleting, there is a hole, like a circular hole. Like once you start increasing the radius of that fillet and it's not touching the hole yet, things are quite straightforward. That's a reasonably easy problem. As soon as that the round's radius is big enough and then it touches that hole, even just a little bit, then you have to handle that case that, okay, now I have a fillet that touches this hole. Like how am I going to resolve that situation? How am I going to change the geometry and the topology in a way that it remains consistent and it provides like a reasonably good solution for this problem? And then once you keep increasing the radius of that fillet, at some point that fillet is going to eat basically the entire hole, and it will like overreach that hole, right? And then you need a third type of implementation for that fillet. And this is not even the hardest problem. Like these are like basic issues that we are talking about. And then basically for in a BREP engine or BREP kernel, you need to cover all of these edge cases one by one. And there's no way around it.
So first of all, BREPs are just incredibly hard because describing the geometry and handling it is just very difficult to do. Yeah. And then you're saying, but then you have every one of these edge cases you have to account for, or else it just crashes and you don't have anything to...
Yeah. So these are just the impossible problems, and then you have the hard problems. And the hard problems are just like everything else. Like just computational geometry is just hard. Like building a robust surface intersection algorithm is hard. Building a robust building any kind of robust geometry algorithm is just hard. It's brutally hard.
What's a surface-to-surface intersection?
So when you are working with BREPs, then most operations will require you to intersect surfaces with each other. So basically identify that curve that lays on the intersection of two surfaces. That's pretty much every single BREP operation heavily relies on surface intersections. Of course, when you have like two planes, it's relatively simple. If you have two planes, the intersection is either going to be a line or it's going to be an empty set, right? If they are parallel. But what happens if they are, even with lines, it's not that easy, because what if they are not parallel, but they meet somewhere far away, right? Where floating point numbers are already like maybe less accurate. And how do you handle that situation? So even intersecting two planes in a numerically robust and stable way, it's not that easy. And then even even when you are working with canonical geometry, so only like with basic geometries like planes, cones, cylinders, everything that is not freeform, even those intersection problems can be like hard, like really hard, and already introduce a bunch of edge cases. Like, for example, let's say that you want to intersect what is the intersection of a plane and a cylinder?
It depends on if you're intersecting the radius or the flat, right? Like the tops.
What is it?
But I guess, okay, so if it's the flat or the top, it's whatever your fuzz distance is. I don't know what the technical term is, but like imagine you have a dot that's like the size of 1 millimeter, like in diameter. You wait until they touch.
But what is the shape of the intersection of that plane and the cylinder?
Of a plane and a cylinder, it's a line. It's a line for the flat, and for a radius, it's a curve.
So basically, even if you are not working with floating point numbers, but you're working with real numbers, even then there are like three different solutions. One is that if the plane and the cylinder are perpendicular to each other, then the intersection is a circle.
Oh, I see what you're saying.
If it's slightly tilted...
Well, no, not a circle, but it's half a circle, right?
It's a circle. It's an infinite plane.
Oh, you're saying...
an infinite cylinder.
So you're saying the entire plane, it's not...
Yeah.
Okay. I thought you meant like...
Not a face, but a surface. So like an infinite surface, like an infinite plane, and an infinite cylinder. Like even if you're working with real numbers, even then you have at least three different solutions. One is that if the cylinder is perpendicular to the plane, then it's a circle. If it's slightly tilted, then it's an ellipse. If it's parallel and intersecting, then you have two lines. Or actually, not even like, here's one more case. What if the plane is tangent to the cylinder? Then you have one line. Or if it's completely like not even touching it, then it's an empty set. So even just for like a plane cylinder intersection, you already have 5 cases.
And so what you're getting at is, okay, well, cool. That's just a plane and a cylinder. What about cylinder and cylinder, sphere on cylinder? So it becomes a combinatorial problem.
Yes, and even that is okay. Like, let's say that we only had canonical surfaces. Even that is brutally hard because we haven't even talked about how to handle all those situations where you have to work with floating point numbers, and you have to make sure that all of these edge cases are handled properly in a robust way with floating point numbers. But let's say that you figure that out, and then you have like the generic problem, and you have two arbitrary surfaces, like a spline, two NURB surfaces, spline surfaces, freeform surfaces. What is the intersection of those two? What is the intersection of those two if those surfaces are already self-intersecting? How do you identify the self-intersecting parts?
What do you mean by self-intersecting?
Like a loop. There's a loop in the surface, for example.
Okay.
And then the surface intersects itself. And
I can't even understand that. So
I mean, just like imagine an shape like an 8, and you extrude it.
Okay.
And it's a single surface.
Yeah.
And then you have a surface that intersects itself.
Wouldn't that be just two surfaces at the point where? Yeah, I'm not understanding this.
I mean, or imagine when you're offsetting a surface that is not a plane and not a sphere, but let's say like a paraboloid surface, right? And as you're offsetting it and increasing the offset value, at some point it will start intersecting with itself.
Okay. Yeah. So it's almost like if you had a U-shaped bracket and you extrude the two sides, the Boolean eventually is going to become one just giant block.
Sort of, yeah.
Okay.
Yeah, but basically it's like this. This is like, and these are I would say that even in this case, like some of the problems are almost impossible, but at least extremely hard. So you have this like set of impossible problems that you just can't solve. So because of that, you can't really build like a fully robust BREP kernel. It's literally impossible because the math is broken. And then you have, even if you build it, it's like so hard that...
So there's no such thing as a solved BREP kernel. It's just you're chasing nines to completeness.
Yeah, it's basically like in terms of like robustness, think of like a logarithmic curve. It's relatively easy to build a BREP kernel that can work with cubes with holes, right? And then actually like a reasonably large number of manufacturing companies are working with relatively simple geometry. Like a lot of the manufactured geometry are actually cubes with holes, right? So and for that, actually BREP is just great. But as soon as you get into the more complex cases, you get into this endless edge case handling. And because of that, basically the robustness of a BREP kernel is increasing logarithmically. So it's because it's all about like managing and handling all those edge cases, and BREP kernel developers over the decades cover those edge cases one by one.
That's actually a really interesting point I never considered. If you were to take something like an iPhone and you look at the outside, that is really complex. You have these very complex, I don't know what's the term, a NURB surface or something like this.
Yeah.
Very sweeping profiles and very complex. But once you look on the inside, it's all rectangles, circles, and extrusions. It's really that simple. And so to your point, most people or most engineers or designers don't really hit the boundaries, but you need to be able to handle them. And then when you do that in a BREP kernel, you just have this combinatorial problem of like many types of problems that you just
infinite, basically. So the problem is that the number of edge cases is literally infinite, because you have to handle all the geometry, topology, change combinations, and because we are talking about geometry, there is an infinite number of edge cases.
So pretend I'm a venture capitalist and I'm looking at investing in a company, and I hear someone like you say, yeah, well, BREPs are very confusing, or they're very, not confusing, but they're very complicated and yada yada. What my answer would be, okay, well, just pick another one. Why use BREPs? Well, like why don't you just use like a mesh, right?
Yeah.
Like whatever I sent to my 3D printer.
Because BREP is the protocol. That's the protocol.
Is the answer really just, well, everyone uses it, so that's what we do?
It depends on your use case, and there are alternative representations, right? There is mesh, CSG. There are implicit geometry. There are a bunch of alternative geometry representations. The question is like, what is your workflow, and then is it okay if your workflow is an island and it's completely isolated from the rest of the industry? If in your workflow you don't need to work with any other CAD system and and the simulation tool and the CAM tools, and you just don't care about compatibility with other tools, then you can do whatever you want. Then it doesn't matter. The question is like, is that okay if you are an island? And the answer is rarely ever yes. It's that simple, unless you rebuild the entire ecosystem from scratch, right? And you build a new representation that and not just that you build a new representation, but you rebuild the entire ecosystem around it. You rebuild CAD, CAM, and CAE from scratch, then you're good. But that's not realistic.
So what you mentioned some other geometry representations, CSG or constructive solid geometry.
Yes.
Why didn't that win? Why in the arms race of geometry definition?
In a way, it did win because basically the way we are doing solid modeling, you can think of it's quite similar to CSG. So CSG is basically this idea that we have a bunch of primitives and we are combining them with Boolean operations. We are subtracting, intersecting them, uniting them, and that's and from the combination of primitives, then we will get a solid body. It's a pretty good concept, actually. It's a really powerful concept, but it kind of fails when it comes to local operations like shells or fillets or face offsets. Those are really, really difficult to express or impossible to express just through the combination of primitives, right? Like let's say that you have a cube and you want to round an edge. What is it like, or not just one edge? Like let's say that you want to round all the edges of the cube. Like what are the primitives that you have to subtract from that cube so that you will have a rounded cube? I don't know. Like it's that by itself is relatively difficult, not impossible, but difficult. But what if I have something more complex? So in the sense that the biggest problem with like traditional CSG, where you're combining primitives, is that it's relatively limited what the shapes are that you can express with a CSG. But basically, when you're doing solid modeling, what you're doing is that you're combining shapes with Boolean operations, and that's how you model stuff, right? The difference is that you're not combining primitives only, but you're combining more complex shapes. And on the top of that, you have these more complex operations, local operations like fillets, shells, blends that can manipulate geometry in a way that would be really difficult to manipulate just with Booleans.
So modification of geometry is really important. So shells or fillets are much easier in B-reps than they are constructive solid geometry.
For the user, yes. For like mathematically speaking, they are enormously difficult to actually implement. But in a CSG environment, you wouldn't be able to implement it in a pure traditional CSG environment.
What's an implicit?
An implicit. Implicits or SDFs, I'm going to use these terms interchangeably.
They're the same name?
They're not exactly the same. So there's a subtle difference between the two. SDF is signed distance field. Implicit geometry is you can think of it as a slightly more permissive SDF, where the distances don't have to be actually like real distances, but like an approximation of the distances. And SDF, but I will use these terms interchangeably. So implicits or SDFs. Like in this conversation, I don't think it matters. It has some implications on the use cases. For example, some simulation techniques require like real SDFs, but in most cases you are just good with implicits. So SDF is a completely different geometry representation compared to B-reps. Instead of representing geometry with its boundaries, it represents geometry with a function that describes, in every point in space, it describes like how far you are from the body that function represents. That's why it's a signed distance field, because when you're outside the body, it will give you a positive number, like the distance from the body. If you're inside the body, it will give you a negative number, like how far you are in the body, and on the surface, it will give you 0. That's the idea. It's a sign distance field. It's a really neat concept that has some really interesting properties. SDFs, for example, like Boolean operations that are famously hard with BREPs and took decades to robustly implement for kernel developers, they are trivial with implicits and free. It's not just that they are trivial to implement, but they're infinitely robust. They can fail, and they are super, super fast. Because a Boolean operation, like a Boolean subtract, a Boolean union, or a Boolean intersection of two implicit geometries, is basically the min-max function combination of the two implicit functions, and that's it.
Well, why can't they fail?
Because basically what you do is like you take basically you have two functions, and then you put the two functions into a min-max function combination of another function. That's it. It's basically like combining two functions through a minimum or maximum function, or the combination of the minimum maximum functions.
Okay.
And there's nothing to fail there. It's like there you can just like write it down, and it's there. It's like,
so what is the input and what is the output of
so the input
function?
is an XYZ coordinate, like in every point in space it gives you a distance. So the input is an XYZ coordinate, and the output is a single number, which is a distance, like how far you are in that point from the body that the function represents.
And it's a matrix, so you know in terms of X, Y, and Z, or vector in terms of X, Y, and Z.
No, basically, like think of in mathematical terms, it's like really like the input is just an XYZ coordinate, right? Basically, like think of you can just type in three numbers, an XYZ coordinate, and in every point I can query basically like how far I am from that body that the function represents, and the function gives me that distance. I type in the three coordinates. I'm here, 1, 2, 3. These are my coordinates in space, and in that point, it can tell me like how far I am from the body. Does this make sense?
Yes, but that is the body.
Yeah.
But what determines the shape of the body?
The function itself. You can basically the function itself describes so the shape is encoded in the function, right? Because if you have the distance in every point in space, you also have the body. Those are equivalent. Now, it's a different question how easy that function is to read, and it's also a different question like how easy it is to display or process or do anything else with it. But that's that's how it works.
Okay. Is this computationally cheaper compared to a BREP?
It's completely different. So it's basically the easiest way. So the benefits of implicits are that most operations that are really, really difficult with BREPs are incredibly easy and fast with implicits. Implicits tend to be very multi-core and GPU friendly, unlike BREPs. BREPs suck at multi-core processing. Like by nature, you can't really process a BREP geometry on multiple cores. It's hard to take advantage of compute, so you can't really solve the slowness of BREPs just by throwing more compute at them. Implicits are infinitely robust. Like all these operations are always they always succeed, and you can always evaluate an implicit function in any point in space with floating point accuracy, if you know the math. So it has implicits have some really nice properties. The biggest issue with implicits is that and why they did not take over the world yet is there are a few issues. One issue is that they don't. It's really difficult to represent sharp features, sharp edges, and regular shapes with implicits. It's really easy to represent crazy gyroid structures, lattices, all these super complex geometry with implicits. But when it comes to this iPhone, what is the distance function of this iPhone, right? It's good luck figuring it out. And I'm sure that you can hack it together in an implicit modeling environment somehow that resembles an iPhone, but it's not a natural workflow. And as soon as it gets more complex, I don't know, like your famous part, for example, you're like what is the distance function of that part? Well, what is it?
It's complicated.
I don't know, like, and to be honest, like nobody knows. So you don't really have this BREP-like workflow, and because of that, representing BREP-like geometry is enormously difficult with implicits.
So edges and workflows specifically are what the weaknesses are.
Yes, and then you have another issue is that, okay, now let's say that you figured out the workflow and you can create these BREP-like geometries with something that resembles a BREP, but then what are you going to do with it, right? So you still have, like, if you can 3D print it, right? If you can convert it to a mesh, you can 3D print it, but then if you want to, you probably want that part to be connected to the existing ecosystem, right? You want you want to run you want to export it to CAM, you want to put it into your PLM system, you want to open it in Annex or Shaper or whatever you're using, right? So then what? And then there are some techniques to convert implicits to BREPs, but typically what these tools do is that they fit a bunch of NURBS patches, freeform patches on an implicit, which, yes, it is a BREP. Technically, it is a BREP, but it's not really usable in another CAD. Like you can't even apply a Boolean operation on them. Usually, you can fillet an edge, or it's like it's a BREP approximation of the field.
So, in addition to the technical challenges like defining things like edges and the workflows that engineers and designers are accustomed to. And by the way, from what I'm understanding, you're saying, look, the advantage of an implicit is that you can use a mathematical function to describe it, and then that gives you a ton of advantage. But as an engineer, I don't want to think in terms of like x squared minus.
Of course not.
Yeah, it's just it's a nightmare. And that's the workflow issue.
So that's definitely an issue. That basically the implicit workflow is based on combining these fields together, and it's not a very natural way for engineers to think about geometry. So that's definitely a problem. But I would say that the benefits of implicits, if I had to summarize what the benefits of implicits are, is that they just solve pretty much all the geometry problems that we have with BREPs, like literally all of them, in terms of scalability, precision, robustness, everything. It's just that there is no workflow to create BREP geometry with them.
But which brings us to the third problem you said, which was just the ecosystem of the world is literally built around the existing technology. So
yes,
you could build you could build the part in a function, and it could be it could be 3 kilobytes, like a tiny little file size.
Yeah.
But then you send it to anyone, and they can't make it because CAM, there's no CAM for implicits.
Yeah.
Okay.
I mean, there is if you are 3D printing, right? Or if you are machining based on a mesh. If you can machine based on a mesh, then it's...
Is that simple because you simply just take the implicit and it's incredibly easy to just convert that to a mesh?
It's incredibly hard to convert an implicit to a mesh. Yeah, meshing implicits is one of the hardest problems with implicits.
Really? I would have totally guessed the opposite.
No, it's really hard actually, and it doesn't really work super well. So there are a bunch of different approaches like Martian cubes and some other algorithms. The biggest issue with all of these implicit meshing algorithms that convert an implicit into a bunch of triangles is that they can't really find the sharp edges. So if you have a generic implicit function, there are a bunch of papers about it, how you can improve these behaviors. But if all you have is just a generic implicit potato without any additional information, if that's all you have, then it's extremely hard to find sharp edges and corners in an implicit, and because of that, it's incredibly hard to find the mesh basically that you are fitting on that implicit. So that's brutally hard.
Why can't you parallelize B-reps. So you said B-reps famously aren't very fast. Like you can't multi-core them, et cetera. And by the way, this has been one of my biggest frustrations as an engineer is that I can go spend $7,000 on a laptop with the world's fastest laptop GPU or just period GPU, and it is no faster than my MacBook running a VM. It makes no sense to me.
I know. I hear you. Yeah. It
Why?
is what it is. Because I mean, it comes down to like computer science. Like not every algorithm can be parallelized, and the way B-reps are, and it's like just like the kind of data structures that B-reps are, those are not very multi-core friendly. And most algorithms that implement B-rep operations can't really take advantage of multiple cores.
Not to put you on the spot, but I've heard Amdahl's law stated in this argument before that and maybe we'll put up a thing, but Amdahl's law just simply states like the performance of a computation is inversely related to the number of things that prevent it from making the next step. I'm doing the world's worst definition of this, but essentially it's just saying B-reps suffer from this thing, that they're not parallelizable because eventually you get bottlenecked by some computation.
Yeah, basically. Yes.
But can you give me an example of a B-rep operation that is commonly locking down the entire system into a single core? Like surface to surface intersection potentially.
It's actually SSI is one of the parallelizable
Really?
algorithms. Yes. Yeah, to some extent. But I mean, eventually, like every algorithm can be like not every algorithm. Like I could give you probably like many examples, and for every single example, somebody could give you like a counter example, but in that case, we can parallelize. But the reality is that in real life use cases, those situations just don't really happen where you can actually parallelize it, and you just get stuck in a part of the algorithm that is single core and can be parallelized, and you're just processing something there for like minutes. Like and especially local operations are particularly prone to these
local operations is in filleting an intersection of an edge, or
like have you ever run into that situation that you were shelling a body and shell just stopped there and it took kind of like 10 minutes for the shell to compute?
Yeah.
Like that's
it's funny, not to go on a tangent, but shell is the one operation where I think Parasolid isn't the best in the world at, interestingly.
Is there a better kernel?
I don't know what it is about whatever powers Fusion 360 or Autodesk Inventor, but their shelling operations are so much better than Parasolid's.
Yeah. So it's an interesting trade-off that Parasolid is more strict with its output. So Parasolid less often creates low-quality geometry. ACES and Shape Manager. So Shape Manager is actually it's a fork of ACES, and that's the kernel that Autodesk is using. Shape Manager and ACES are much more tolerant. They will do whatever you ask them to do.
But they don't care about being right.
Yeah, you might end up with something that is like a little bit like maybe not that great. Yeah.
So can you expound on this? There's probably three things that have terrified me about what I learned about the world after becoming an engineer. One of them was learning that B-reps, that the output from a B-rep kernel, i.e. any CAD application today, could be totally different depending on which one you use to compile.
Of course.
This is crazy to me. So you're saying I can take the exact same shape, shell it in NX, and then the output from Autodesk Inventor would be totally different potentially.
Yes, of course, especially if it's a thicker shell where the topology is changing more dramatically, then yes, absolutely. Like again, like it all comes down to how the kernel manages the topology changes, and again, there isn't like a silver bullet for handling topology changes, and because of that, every kernel implements it differently. So yeah, it's very much possible that you end up with completely different results. And it's funny because because otherwise, like mathematically, shelling is one of those operations that has like a clear definition, like what the expected output is for a shell operation, right? You want a unified thickness, and then you want a few faces removed, and that's what you want, right?
And yet, and to me, this sounds so easy.
Oh yeah, with implicits, it is actually like offsetting, and because of that, shelling is one of the easiest operations with implicits, because if you're shelling an implicit or offsetting an implicit or SDF is literally just like adding a constant to a function, because that increases or decreases the distance function in every point in space, which is the definition of thickening.
This might be a dumb question, so if it is, don't answer it. But can you literally say out loud what the implicit function that describes a cube is? Is it that simple?
A cube, maybe not a cube. Cube is relative. It's a little bit more complex.
But a sphere would be easy, right?
But a sphere is easy actually. Like, but even you could like formulate the implicit function of a sphere. Like, can you come up with that function in your head? Like, what is the given the the center and the radius of a sphere? Like, what is the distance from that sphere? It's quite easy.
What would be? Can you like? What is it? Is it just r cubed? Like what?
No, it's basically basically it's the distance between the center of the sphere and that XYZ point, and you have to like subtract basically the radius of the sphere from that.
Okay.
Like, just imagine a sphere that's at the center, like it's at the origin of your coordinate system. Like, what is the distance in any point in space? It's quite easy to determine that distance from that sphere, right? Because it's really just like the distance from the origin, and you subtract the radius of the sphere.
Okay. Understood.
Does it make sense?
Yeah, I think the thing that confuses me as a layman is when I think about a B rep, I kind of understand it because there's no reference frame that I really care about. It's here's 4 or 6 surfaces that describe a cube.
Yeah.
Doesn't matter where I'm looking at it, like that makes sense. But with implicits, it sounds like, well, you have to have a coordinate system start, which of course you probably need in B reps. I just don't think of it that way.
There are probably like 100 different ways I could formulate a cube's implicit function. It's not, and there isn't like a single obvious way.
This brings me to the next question, which is, what do you think about text to CAD? Because we're talking about these really incredibly complex geometries. And I'm curious to hear what you think about it.
I am a little bit reluctant to
talk about it.
Not even to talk about it. I don't know what is text to CAD. It depends, right? Because first of all, I'm an AI maximalist, like 100%. Like I'm a big supporter of all the frontier labs through my token spend. So and
what's your token spend?
It's significant. I prefer not to say, but it's significant. And we have seen some incredible incredible results, like shrinking like 10 years of software engineering into like literally to a few months kind of results. So I'm an AI maximalist again. But obviously I'm a little bit concerned about text to CAD, at least about those concerns or those concepts that I'm seeing as text to CAD. So, and when I say text to CAD, so this is very important. So I'm going to define what I mean by text to CAD when I talk about it. What I highly doubt is that we are heading into this future where, you tell Claude, design me a car, and Claude will design you a car. So that, and then it comes up with a rough design, and you just like keep prompting it, and that's how you fine tune your design. So I think that idea is just like the entire concept is broken simply because natural language is just not the right interaction model for geometry. If I created 10 pages long description of this mic, every single detail. And then I handed it over to 10 different designers. They would come up with 10 different designs, right? Why would LLMs do better at that? So I have this like, which, and again, it doesn't mean that LLMs are not useful for CAD design or for manufacturing. They are incredibly useful. It just, this idea that we are just going to prompt our models, that doesn't, I don't think it solves any problem. And I also don't think that it makes any sense. So that's a nonsense.
Who's going to break it to the 1,000 text to CAD startups right now that this is not a good idea?
I mean, I did, I guess. And so I'm super skeptical about that direction. And again, I'm super bullish on AI. We have some, I think, some really good ideas like how to use LLMs for design, engineering, and manufacturing. But it's not. I don't think that the future is like plugging in Claude into existing CAD systems. I think you need a fundamentally different architecture.
What does it feel like? I mean, how long has Shaper 3D been around now? It's been almost 10 years?
8, yeah. 8? It depends on how you count it. 8, let's say 8, yeah.
You've been slaving away at this problem for 8 years. And in the last year, you've seen just this onslaught of new CAD companies.
Yeah. I was very excited about it. It's really cool.
Really?
Yeah.
You don't see it as, like you don't get frustrated or annoyed by this?
Frustrated by what? Like why?
Well, maybe this is, it just seems like it would be frustrating to work really, really hard on a problem and see people appear and think, oh, well, I'll just fix it. Like, clearly they just couldn't figure it out.
That's how innovation works. Like, I mean, that's how I started Shapers. What's not to like? I mean, it's great. Like, let's go, really. And I mean, I'm really happy for everyone who wants to build great industrial manufacturing, engineering, design software. I think it's great. Really, it is.
But
it is. Yeah, sometimes yes, and sometimes the ignorance of newcomers can be frustrating. But to be honest, like this industry has always been full of people building products that don't solve a single customer problem. This, like, if you ask anyone who has been around for a few decades, if you ask Carl Bass, right, or you ask like John Hirschtick, if you ask any of the big CAD guys there, they will tell you that in the last 30 years, or since CAD exists, this industry has been always full of people building technologically interesting problems, technologically interesting products that are not solving any problems.
It's funny you said that. Carl said the same thing.
I don't disagree with Carl. I agree with him in a lot of things, actually. Yeah, it's very common.
So what would you say to people entering the space then? If you, because clearly the energy, I think you're rewiring my thinking on this. I shouldn't look at it as, oh, well, they're just trying to diminish what I'm doing. Instead, you should look at it as these people are excited about trying to solve problems in the space, in a space that needs problem solved.
Yeah.
Right? What would you say to them instead? Or what would you say to them if you could give them some advice?
Work with design partners who actually will tell you what to build, and like sit in their offices and just like don't leave until you have a product that actually solves a problem that they are willing to pay for. It's like I think market, not even market discovery, but like understanding this space is. So there are two different types of founders that I see in this space. One is the software guy who thinks that we just crack CAD, right? Oh, let's go. We will write a BREF kernel. We'll write a BREF kernel and we will vibe code a CAD on it and we will take over the world, right? So, so the software founders typically have zero idea about anything related to manufacturing or engineering or design. they make up problems. They think that, oh, there is this, SaaS company, that did this and that. We are just going to do the same with manufacturing software. And then they build it and then they fail. Every year you have probably 100 of these people starting these companies that never really go anywhere. And then you have the other type of founder who is an engineer, like mechanical engineer, has a background in manufacturing, but I think they typically fail in two different ways. One is that either they are trying to solve a problem that only they had, and they just over obsessed with their own problem that turns out to be an extremely niche problem that doesn't really exist outside their world. And the other problem they have is that they don't know how to build software, and they don't know how to build a software company, which they can learn, of course. And I think it's probably, by the way, I think it's easier to learn how to build software for a mechanical engineer than learning manufacturing for a software engineer. So I think these type of founders have they have an advantage. But I think if I was a mechanical engineer starting an industrial software company, I would try to find a really, really, really solid software engineer who will build with me. But I think on average, they are better positioned to build something meaningful simply because for them, it's just easier to understand their real problems. Yeah.
Why is this space so hard? And when I say this space, I mean CAD and engineering software. It feels like B2B SaaS, and for the engineers out there with real jobs, B2B SaaS is like software as a service that you sell for a monthly subscription or something like this.
Yeah, I think there are a few reasons. One is that simply that the technology that you have to build is just hard. It's not, most SaaS companies are building software that is virtually they slap a web front end on a database and that's a product, right? It doesn't really require any highly sophisticated computational or computer scientists or mathematicians or physics PhDs. It's relatively basic, easy software engineering, typically connecting existing software components, and that's the product, right? CAD, CAM, and CAE, you need math PhDs to solve our problems. You need really the most hardcore folks. So and I think that's already out of the comfort zone of most software people. Probably 95% of software engineers are just they can't really build software like this. So that's one problem. The other problem is that CAD, CAM, CAE are one of the oldest software in the world. CAD, CAM, CAE is probably the oldest software industry in the world that remains undisrupted since the 1990s, right? And because of that, there are basically no greenfield areas. Every single problem that is relatively easy to solve and can be solved on the current technology stack is already solved. So unless we see a technological breakthrough similar to what AI is for the broader economy, I think it will just remain extremely difficult to build a really large company in this space because the capabilities that you can provide to your customers are fundamentally capped by the capabilities that the existing ecosystem and technology stack can provide. Because of that, finding the problems that are extremely valuable and nobody else has solved is just hard. And I'm not saying that there aren't any. I think there are problems that you can solve that are valuable and can be solved on the current technology stack, but those are non-obvious problems, and I think just finding those problems is just hard. And then another problem is that there isn't really a lot of money on the mid-market. So you either go after the most sophisticated high-end startups with a lot of funding, or you go after enterprise companies. So now a founder who understands manufacturing, can build software, and really good at enterprise sales, it's again like you again like further limited the pool of people who can be successful in this space. Yeah, I think these are probably the three biggest limiting factors. I think this industry, like unlike every other or most other software industries, has not really seen a major technological breakthrough for decades. Actually, one of the most promising breakthroughs in the 2010s was direct modeling, your favorite, right? And direct modeling, like the promise of direct modeling at the time was that, okay, now we are going to completely reinvent how CAD works, and it will solve all the like compatibility problems and robustness problems of CAD, and this is the future. And then it did not take off. So yeah, it's hard. So even when a breakthrough comes along, it's like the market adoption is again not trivial.
So part one is it's one of the most difficult computational challenges. It's one of the most difficult software engineering problems.
It's very hard, yes.
Okay. The other one is it's actually one of the oldest software industries, parts of the software industry, which I never realized, but you're right. Like it's what, COBOL mainframes for the financial industry from the 60s and CAD. Like I think this might be, manufacturing software might be the oldest one or one of the oldest.
It is literally probably the oldest one. I mean, one of the first computers that John von Neumann built. Why do you know why was that computer built?
Was it for the Manhattan Project?
Yeah, and it was for computational design. It was a computational engineering problem that they were trying to solve, or that they solved with the computer that von Neumann built.
Did they actually use a computer for the... Really?
Absolutely.
Wow.
Read the book, The Man from the Future.
Okay.
Very good.
So it's just a very hard problem to solve. It's an old industry. And then finally, you said that the mid-market, there wasn't much money there. Could you explain why that is? Because to me, it seems like the bottom of the market would be kind of the worst place to be.
How many seats? So most industry analysts separate the market into two big market segments. One is the mainstream market, which is like SolidWorks, Onshape, like the mainstream tools, SMBs typically, and then you have the high-end market enterprise. That's typically basically the big three, right? Creo, NX, and CATIA. In the mainstream market, the average seat per customer for most vendors is a lower single-digit number. So the average spend per customer it ranges from a few thousand to a few 10,000
per year.
Yeah. So that's famously the valley of death in sales, because the deal cycles are going to be relatively long, because these are fairly well-established companies. They will try to evaluate. They want to evaluate your solutions, and so on. And their budgets are relatively small. So that's just not ideal, right?
And you're talking about small to medium-sized businesses right now? Mm-hmm. Okay. So you're talking about like engineering firms of 1 to 20 engineers.
Yeah, like the typical SolidWorks customer, right?
Okay.
I mean, SolidWorks has bigger accounts, of course, but it's not a typical enterprise tool. That's not where the majority of their business is coming from. And then you go up to the high-end market, like how big the biggest and like CATIA, NX, Creo accounts are. Like, what do you think? Like, just ballpark.
Hundreds of millions of dollars, and I think that's probably not the largest number if you went to the right organization.
No, it's probably it is like hundreds of, like a couple $100 million that's a real number. There are, and that's a single account, right?
And it's larger than like the GDP of some countries.
I don't know which country that is, but yeah, like these are, yeah. So in enterprise you can go really, really big, but then you have all the problems that you have in an enterprise company. It's just difficult for a startup to crack the enterprise market.
So
not impossible, but it's difficult.
So there's this valley of death where, because it's only $2,000 a year on a seat, and it's so hard to win a customer. We haven't talked about why yet. We should also talk about that. I think I have some ideas around that. I would like to hear yours. Because it's so much work and the return is a couple K a year, you have this failure to launch. You could go straight to enterprise, but winning a $10 million contract it's incredibly difficult.
Yeah.
And so why isn't that the business model? Why isn't, anecdotally, from what I understand, Onshape now has been around for more than a decade.
Yeah.
And they still have yet to crack 1% adoption of the market, the total market, from what I understand. That number is just what I've heard. I don't know if it's true or not, but I know it's not 5%. And then a lot of money has changed hands to make that software.
I mean, I don't know anything about Onshape. I've been not really following them closely in the last few years, since they've been acquired by PTC. So I don't know. I can't comment on that. But Onshape or not, there have been definitely many attempts to disrupt the CAD industry and build something new. And all of those attempts were not very successful, at least to say. Or not very successful in the sense that we have the same oligopoly that we had 30 years ago. It's Siemens, aka Unigraphics, Dassault, and PTC, right? And you had basically the same, literally 30 years ago.
What was PTC selling 30 years ago?
Pro-E.
I keep forgetting that that's a real package.
Pro-E.
Yeah.
That's not a real package because they rebranded it to Creo.
I've never met. Yeah.
Creo, like they decided, I don't know, 10 years ago that Pro-E is now not cool and it should be called Creo. So now it's Creo.
You know, believe it or not, I met someone the other day who actually likes Creo.
That's cool.
Yeah. Sorry, I interrupted.
Nice. Yeah. Well, it definitely has many advantages. I mean, the Granite kernel is arguably one of the best, or probably the only kernel that is as good or comparable, or maybe even better in a way than Parasolid. If you talk to people who actually worked on Granite and worked on Parasolid, or worked with Granite and worked with Parasolid, they will tell you that Granite is probably the best kernel on the market.
So the developer experience with Granite is better than...
Not the developer experience, it's just the robustness and the scalability of
the actual
Granite.
product of the kernel.
Yeah.
Okay.
Yeah.
So I haven't... that's interesting. I haven't heard that. So why isn't it more popular? It seems like Parasolid pretty much powers the entire planet at this point.
Yes, true. I mean, I think Siemens did a fantastic job with commercializing Parasolid. If you think about it, when you and also like there's this interesting like network effect that the more tools use Parasolid, the more it makes sense for you to start a company based on Parasolid because you will be more compatible with those tools, right? So I think Siemens did a really good job with commercializing Parasolid. It was a highly non-trivial and highly strategic move when they decided that they will license Parasolid because they could have just kept it for themselves, right? But they decided not to, and they are licensing it, and they are famously very proud of the like how open they are and the level playing strategy of Siemens, or that they are creating this level playing field where everybody starts with Parasolid basically, and with D-Cube, then everybody has the same technology, and then really your success only depends on like what you build on that, right? So I think in that sense, Siemens has been like an incredibly incredible catalyst of the ecosystem. But it's still BREP, right? I mean, it's and Yeah, yeah. And it's like, it's interesting that it doesn't really matter what BREP kernel you are using. Every BREP kernel will fail roughly at the same rate, will scale roughly to the same scale. And again, that's because they are running on the same math, the same mathematical concept. And like, until we figure out something better, I just don't think that we will see like revolutionary breakthroughs in CAD, CAM, and CAE. It's interesting that how important the geometry piece is in this ecosystem. Every single tool's capability highly depends on, like including CAD, CAM, and CAE, highly depends on how well, how robustly, and how fast they can process geometry. Because eventually, like, you're representing the physical world with a geometric representation, and all of these tools depend on geometry processing. So if there was something better, that would mean that pretty much everything like CAD, CAM, and CAE becomes better overnight. But then you still have this like lock-in problem. Like, what are you going to do with it? If it's an island on its own and you have to rebuild the entire ecosystem, then it's not going to happen. So it's an enormously tough challenge, highly non-trivial, partly because the business problem, the underlying business problem is really difficult. And the product problem and the technology problem are also extremely difficult.
So when we talk about why this industry is so hard, for going back to the example of, okay, well, if you want to enter the industry, you pretty much have to focus on winning a whale. You have to go get one of these big enterprise contracts. Is that one of the key problems, that at the end of the day, you're locked into the existing technology because that's what the entire ecosystem is built around?
Yeah, it's definitely a problem. And when I say that you have to go after enterprises, I think what I mean by that is if you want to disrupt the CAD and the CAE market, that's what I mean by that. I'm sure that there are many unsolved problems for SMBs, manufacturing SMBs, that you can solve. And maybe you can build a successful business on manufacturing SMBs, but not in the CAD CAM, not in the CAD CAE space. In CAM, probably yes. In CAM is SMB.
CAM, for some reason, seems to be there's more opportunity there. I don't understand CAM enough to really understand why, but it does seem like startups are getting more traction. Companies like Toolpath, or I guess they were acquired, but I think they were. I'm not sure. It seems like the CAM industry is easier than CAD. I don't know if that's true or not.
CAM is easier than CAD?
Yeah.
Oh, definitely not.
Really?
It's the former VP of product of one of the big CAD companies once told me that, István, CAM is just too hard for a CAD company.
CAD is the hardest, I thought.
Never go there. It's like, okay. And it's a very difficult market, highly fragmented. Now, actually, Autodesk has been doing a fantastic job with Fusion and Fusion CAM. Like, Fusion is an incredible CAM tool and highly affordable, right? So they have been consolidating the market quite a bit. They are doing like rip and replace deals.
This has really surprised me. Every time I walk into a machine shop now, I pretty much see Fusion.
Yeah, totally. Like, they are killing it. It's fantastic. And I think the product is also great. It's not just a great go-to-market, but the product is also fantastic. Fusion CAM is great. And also the CAM market it's relatively small.
Yeah. Can you say any numbers about what the TAM, or the total addressable market, is for CAM and what it might be for CAD?
Oh, I will get a lot of crap for this because everybody there are different ways to look at it, but I can give you ballpark numbers. CAD, depending on the segment, and again depending how you look at it. So SolidWorks as a company is making around like $1 billion a year, and annual customer spend on SolidWorks is probably closer to $2 billion, including everything, than $1 billion, because they have VARs that take a cut and so.
Oh, right.
So SolidWorks represents roughly 40% of the mid-market or half of the mid-market. So that puts the mainstream market somewhere between, again, depending on how you look at it, somewhere between like 3 to 5 billion, I guess, maybe 3 to 6 ballpark. And then on the high end market, the two big ones, so CATIA and NX, make not just, and this is not just CAD, but CAD, PLM, everything. So Siemens Digital Industry Software and Industrial Systems. It's quite similar. It's like 5-6 billion a year, both. And then you have PTC, which is I think another 2 billion. So that's the high end market is around like 15 to 20 billion, maybe, again, depending on how you look at it. And CAM, that's again probably like single digit billions, like lower single digit billions.
So not only do you have the exact same problems with CAD, but it's also 10% the size, something like this?
Yeah, I mean not 10%. I don't know the exact number for CAM, but it's a highly fragmented market. I don't know the exact number for CAM. Like my ballpark estimation is that it's lower single digit billions. I would have to look it up.
Okay. So changing gears, what is parametric modeling?
Oh, you're getting there.
We're going there.
So parametric modeling it depends, right? Because at its core, like in its purest form, parametric modeling, the only thing that parametric modeling means is that I can programmatically create a model and I can drive it with parameters. That's what it means. I have input parameters that I can change and my model is going to update based on those parameter changes. So I can drive certain parameters of my model with inputs and then it will generate the geometry for me automatically. That's what parametric modeling is. And then there are feature trees, which are the implementation of parametric modeling in most CAD systems that you hate, right?
And just to be clear, the two are often conflated. People think that, SolidWorks or NX, they have a feature history, and that feature history is parametric.
Yeah.
When in reality, you can actually have a non-parametric feature history.
I mean, you're playing with words here. It's like,
But
we can do the autistic engineer thing, and it's like,
well, actually,
no, that's not really parametric, and I don't like it. So it's more like what it really depends on like what every vendor came up with their own terminology. So I think we can just go back to first principles and define our own. Yes, like feature trees and parametric modeling are not the same, right? You can generate geometry from code. You can write code that will generate geometry, and you can drive that model with parameters, and you can change parameters in your code, and that's also parametric, right? In that sense. So yeah, these are not equivalent. Feature tree is the point and click simplified version of parametric modeling, basically, that gives you one advantage over just writing pure code, that it gives you this mechanism that is called topology tracking, which sounds like a great idea, but it's actually pretty awful, and it's the root of all evil, and that's what makes all parametric models fragile. So topology tracking is this mechanism that assigns a unique ID to every single face and edge in a model as you're modeling. And after every single modeling step, a topology tracking algorithm assigns this unique ID. And it's not just that these IDs are unique, they are persistent, which means that if I re-evaluate my feature tree, if I rerun the code that defines my model, after every single evaluation, doesn't matter like how many times I evaluate it, the same IDs will be assigned to the same topologies every single time. So if I have a cube where here I have Johnny the edge, right? Then it will get the exact same name every single time, no matter how I change the input parameters of that cube. So this mechanism makes it possible to do things like local operations that update properties. So if I have Johnny the edge, I can apply a fillet on Johnny the edge, and every single time when I change the cube, that edge is going to be filleted. That's the idea. It's brilliant, right? So,
But
the devil is in the details. So the devil is in how this is actually implemented and how it works in practice. Do you know how it works?
let's do it. Tell me.
Okay. So let's say you have like a sketch, like a rectangular sketch. That's the first step in your feature tree. And then you apply an extrude operation. You have a second step in your feature tree. And then you select this edge, one of the edges, and then you apply a fillet on it. You have a filleted cube where just one edge is filleted. So you need to solve this problem that every single time when I change something in my feature tree, I have to assign the exact same ID to that edge so that I can apply the fillet on the same edge every single time when I change the cube. The way this works in traditional CAD systems is that basically every single topology gets the ID based on its creation history, based on their lineage in the feature tree. So the name of that edge, the persistent ID of that edge, is going to be that this edge is the edge that was created from this sketch element from this extrusion, where the top edge of this extrusion that was created from this sketch is the name of this edge. Does this make sense?
Yeah.
So basically what you are tracking is that for every single element, like what is their creation history, and the ID of that face and edge is like basically the history of their creation. That's what you are tracking. Now this sounds fantastic, right? Because it feels like this will give you like a very sticky ID and what's not to like. And it is a really neat concept which works really, really well until something gets split into two, or two things that were separate are merging into one.
Or you wanted to remove a constraint, but it wouldn't remove, so you deleted the geometry.
Or something disappears
Yes.
that was there. Yeah, like basically these are the three main reasons why feature trees break for topology tracking. So and again we get back to this like problem of B-rep modeling, that just like with B-reps, there are a bunch of problems that cannot be resolved simply because there is no good solution. These problems can be resolved with feature trees either. So if you are using this lineage-based tracking for topology tracking, then you will always run into this problem: is that how can I handle this situation when two separate entities get merged, or when a single entity gets split into two, or what happens if something disappears that I referenced in my feature tree. And there is no good solution for these problems. There's simply like no good solution. And that's the limitation of feature trees. And that's why your feature trees break. Or that's why your feature trees break because of topology tracking. And the other reason why your feature trees break is because B-reps break. So even if you built a robust parametric model and all the topology tracking is robust, even then it might break because the B-rep operations will fail.
So can you have parametric modeling without a feature history, or vice versa?
Code, like you can build a model from code, right? And actually, so the problem with that is when you're writing code, and you're modeling from code, how can you pick a face or an edge? So if you're driving your model purely from code, like how can you just click on a face, click on an edge, and select that and apply a fillet on it? If you want to fillet an edge, or if you want to shell a body and select a bunch of faces, how can you do that when you're driving your model from code? You can't. You have to so that's one of the bottlenecks for modeling from code. The other issue, but at the same time, by the way, if you drive your model from code, then you suddenly have a completely different tool set for topology tracking, because suddenly you don't necessarily have to rely on topology tracking, because unless you built a feature tree in your code, then you don't even have it. But you can actually create selections based on code, right? And you can, let's say, like you can do stuff like pick every edge or fill at every edge that is shorter than 5 millimeters and have these and these and these properties, right? Or draft every single edge that separates, fill out every single edge that separates a drafted face from a non-drafted face. How can you do that with a feature tree? You can't, probably. And then these are real world problems. That's why I'm actually quite excited about this idea of CAD as code. Let's say that you are designing molds for injection molding, and you need exactly this operation that you want to fill out every single edge that separates a drafted face from non-drafted face, like a proper mold designer would, right? Every single time when your model is changing, for which you're designing the mold for, every single time when the model is changing, you have to manually check if every single edge is properly filleted. That has to be filleted, right? If CAD was a bit more like code, then suddenly you can solve this problem, right? And actually, CAD as code is not a new idea. It's been around for decades. It feels a pretty natural direction for CAD. The biggest problem with this idea that CAD should be code has always been that writing code was really hard. And now that writing code is really easy with LLMs, now I think there is a window of opportunity now to make this long-lasting promise a reality and create new workflows that are more like that they're shifting parametric modeling a little bit more towards code, or at least make it possible to fully control your parametric model when you need it, right? So I don't think that feature trees are completely bad concept. I think they have their place. It's just that they are limiting when you are trying to build truly parametric models. And you're right, by the way. I think that very often you just don't even want to build a parametric model. You are okay without the feature tree, and you're just okay with direct modeling.
What is direct modeling?
So direct modeling is when you are modifying the geometry through local operations, mostly, or not even local operation. When you don't have a feature tree, and you are modifying the geometry through directly instead of changing the feature tree. Basically, there are direct modeling is not exactly new, right? Like classic direct modeling was the original way of 3D CAD modeling in the 1970s, 1980s. But in the 2010s, a company called SpaceClaim, founded by my good friend Blake Corter, invented direct modeling. And basically what they figured out is that how can I apply certain kind of changes on BREP models that are only possible, or that were only possible before with a feature tree. For example, they figured out how can I grab a face in a BREP model without having a feature tree. How can I grab a face and just move it in the model? That's pretty cool. That was completely impossible before. And they figured out how can I not just move faces, but how can I rotate them? How can I basically on a face by face basis, how can I apply modifications like offsets, face move operations, without breaking my model in a highly intuitive way? So this, and it turns out that direct modeling is actually quite handy because first of all, it's super fast, and it makes it possible to apply certain type of modifications on geometry that would be enormously difficult with a feature tree, or when you just don't have the feature tree simply because you're working with imported geometry. So that's what direct modeling is basically.
I didn't know the story behind Blake at Space Claim, that it was even as recent as 2010. So I thought it was later than that, or more earlier than that. To do that, how did they do that? Because it seems like those operations are driven at the kernel layer. So it's almost like you'd have to write your own kernel, and I'm sure they didn't.
Yeah. So Mike Payne, who was the co-founder of SolidWorks and was the co-founder of PTC, started Space Claim with Blake. And they licensed ACES, and they had source code access, and they hacked direct modeling into ACES. As far as I know, like from what Blake told me before, like Mike Payne just fixed all the bugs in ACES single-handedly.
So they just took two computational engineers, gave them a bunch of Red Bull in a couple of years, and then just figured out how to make direct modeling a thing.
Yeah, so sort of, yeah. Yes, and they just hacked it into ACES. And then everybody else did it, right? Then Siemens built it into Parasolid, and they even commercialized it, not very successfully, right? They have this mode in NX called synchronous modeling, which is a fancy name for direct modeling, basically.
Which, by the way, that is one of the most frustrating things I've seen in the industry, because I have to explain to people, no, you are direct modeling. It's just this other name. It's very, anyways, sorry to interrupt.
Yeah. And then there's Creo Direct by PTC. So now everybody is doing it.
Yeah.
But it remained super, super niche. Siemens actually put in a lot of effort into making synchronous modeling successful. I don't think that anybody understands what synchronous modeling is today. It's like serious. I'm one out of maybe like 10 advanced NX users. One actually understands what direct modeling, what synchronous modeling is.
Wait, when you say that, do you mean they understand what synchronous modeling is in terms of like they knew what the name was, or synchronous modeling you're saying is different from direct modeling? And
No, I think they're like maybe 1 out of 10 advanced NX users who actually use synchronous modeling and understand it and integrated it into their workflow. It's like it remained a niche.
This was really surprising to me. So I direct modeled because I just had bad practices and was in a rush, and I didn't care to make parametric models. And then I got into the consumer electronics industry and realized that actually all the really expert users are paying for NX because you get the world's best direct modeling tool. And they're really at the highest echelons of engineering, as far as I can tell. They're actually direct modeling and not parametric modeling.
Yes.
In some cases, not all.
So yeah, I think it depends on the industry, right? And it also depends on the use case. And yes, there are. It's more like a religion than I think. Seriously, it is a religion. It's like there are like diehards, the direct modeling fans and parametric modeling fans. I think, and you're right that direct modeling is much less computationally intense, and sadly, because of VREPs, no CAD system can handle large assemblies really well. But quite frankly, I think that's probably one of the biggest arguments for direct modeling, that because VREPs suck and they don't scale, if you're working with large assemblies, then the trade-off that you are getting is probably just not worth it. But let's imagine this like perfect world where we have this miraculous technology that just scales, I don't know, like orders of magnitudes better than BREPs, and you don't have all the like performance issues, and then you have, I don't know, like a way to build like truly robust parametric models that don't actually break and actually update the way you want it.
You fix the topology naming problem.
So that's if we fixed all these foundational issues, then I think like parametric modeling is just like natural. It's a better way of modeling.
I disagree with you, because the fundamental problem with parametric modeling, from my perspective, and again, I actually do agree with you in that it is a matter of preference. I think everyone's wrong, and my preference is right.
Of course.
But it's probably a matter of preference. The problem with parametric modeling is, even if you fix all those problems, if you design a satellite and you say, I want to change that edge right there, go find it in the feature history tree. It's going to take you hours, right?
Yes, and that's why I'm saying that I think it's not either or, but it's both, and I think it depending on the use case and the situation, you have to pick the right tool.
But here's the crazy thing. In all of my experience in industry, I've never been allowed to do both. Or I shouldn't say allowed. The official practice has been you pick one and stick to it. I rarely see that they allow both.
Yeah, I can understand why that is. So, yeah.
So can you give an example of where you think clearly parametric modeling wins and it should be deployed and an organization should be using it?
Again, I think about it in a little bit more granular way. So I don't think that it should be like an organizational policy. It should be a use case policy. And for some use cases, I think you want to have direct modeling, and for some use cases, you want to have parametric models. But I also agree that it doesn't really make sense to build parametric models that won't really update on parameter changes, right? So that's true. But if I want to make an argument against direct modeling, then simply just like changing complex fillets and complex shells can be really, really, really difficult or impossible with direct modeling, and then you just have to manually rebuild it. Or you really well understand how direct modeling works and how you can delete that set of faces that you have to delete, and then you can do your like magic direct modeling and restructure the BREP basically manually in a way that the BREP the direct modeling operations will do what you want, right? So, but since you are a hardcore direct modeler, you know, like direct modeling is not a silver bullet.
You actually get a sixth sense. You can actually sense what an operation will do before you do it, and that is how you direct model.
Yes.
In the fillet example, like in the worst case where you have combined fillets, you kind of have to be able to think three steps ahead.
But sometimes you just can't delete a fillet. Because it's not possible with direct modeling, because let's say you have two complex fillets that basically like merged
with BREPs. It's a BREP problem.
Yeah,
right?
of course.
Yeah.
But you have two complex fillets that merged basically, and they ate the face basically that was surrounding those blends. Then you just can't delete it anymore. So and then yes, you can get into like sculpting mode, you know, and add some material around it and like boolean it out, and it's like so you can. And I understand that there are workarounds, but again, I think it's not less problematic in those cases than parametric modeling is. And in exchange, with parametric modeling, changing a blend is trivial, right? Or changing the wall thickness of a shell is trivial if your BREP kernel actually works for that shell thickness. But
well, can you give an explicit example where you would say, okay, this use case should be parametric modeling, should not be direct modeling?
I think if you're mostly working with relatively simple geometry, canonical geometry only, you don't have very complex fillets. Every fillet that you apply is clean. There are no overflowing fillets. There are no brutal topology changes. I think those parts are better off with direct modeling, because direct modeling is really good at working with canonical geometry. So it's really just like plain cylinders, cubes, like so simple geometry, which is, and again, you're right. That's probably like there are a lot of use cases like that. Like maybe like most parts in the world are like that. But as soon as your geometry is more complex, you have these more advanced fillets, more advanced shells, more advanced surfaces, for example. Then I wouldn't want to rebuild my entire surface model skeleton from scratch because a fillet doesn't update, right?
Yeah.
So
so for simple parts or simple assembly, well, not simple, but things where you clearly don't have a lot of complex filleting or surfacing, that would make sense.
Yeah, I think it really depends on the geometry. If again, like after probably a few years of direct modeling, you can tell if a part is direct modeling friendly or not, right? And if it's direct modeling friendly, then I think you're probably better off with direct modeling. If it's not, and another really difficult problem, by the way, with direct modeling is patterns. Like, what are you going to do with patterns?
I will admit defeat there.
So, like
Hole patterns specifically, if you counterbore a hole pattern, or the worst one is flatheads where there's a slight flat, like a counterbore recess on it. It's just a nightmare. I agree with you on that. But actually, you say that, but with the parasolid kernel specifically, and in your application, you've made it so that you can actually pattern faces that become a part of the solid, which makes that way more tenable. You can just delete and then quickly pattern again. It's really nice.
Yeah,
it's a workaround.
And pattern again is so nice. I love it. It's like probably not, right? So it's like if I want to change just the number of the patterns, I prefer to just change the number. So
that's fair. Do you consider CAD a solved problem?
Well, yes and no. Like, I think in its current form, it's probably solved. And again, I have this strong belief that the capabilities that today's industrial software can provide is fundamentally just capped by the technology stack that we are running on. And everything that can be built on BREP have been mostly built.
So we've chased all the nines essentially in BREP representation.
Yes.
Do you think that BREPs have held us back?
In a way, yes. And again, like you can make this argument that most of the thing, like, and I mean, look, it's not black and white, because 16% of global manufacturing, 16% of global GDP is in manufacturing.
60?
1/6.
1/6.
Yeah, 1/6, 16. And that 16% is produced by BREPs, right? So that you can't really say that that's bad, right? It's actually it's pretty cool. Like literally everything that we manufacture today is based on BREPs.
Well, I mean, it was pen and paper 60 years ago.
Yep. And that was also great. And then CAD arguably opened up new workflows, right? Not like largely because we have, for example, simulations, right? If we did not have simulations, if we could not run like an FEA on a model, how much less valuable CAD would be? Probably much less valuable, or 3D CAD, right?
So you're saying if we didn't have things like FEA, then the value of CAD wouldn't be really with it.
That's not what I'm saying. I think it's just like how much, maybe like half of the value of 3D modeling, GDP value is coming from the fact that we can analyze the geometry in ways that is impossible to do on pen and paper, right?
So it's not about, I see. So you're saying the value of CAD and BREPs in the current incarnation, or at least just the representation of geometry on a computer, is that you can feed it into FEA, you can feed it into CAM, and you get all these knockdown benefits.
Yeah. So basically, it's not just CAD, but the downstream workflows that we can build on CAD, what make the BREP ecosystem enormously valuable. So I wouldn't say that BREPs are bad, right? Because that would be stupid, because BREPs are powering 16% of global GDP. So it's pretty decent, right?
That number feels a little lower, weirdly.
Was that?
16 seems low.
That's the number.
Yeah. Sorry to interrupt.
Yeah. And then, but I firmly believe that we can do better and we should do better. So just because we can produce 16% of GDP with BREPs, that doesn't mean that we could not produce and like 25% with something better, right? So I wouldn't say that BREPs are fundamentally limiting, but I think BREPs are not limiting the current workflows, because the current workflows are built around BREPs. But if we could just get, so let's say that let's just look at some of the BREP bottlenecks. Large assembly management. How would the world change if we didn't have to do large assembly management anymore? Because all of those issues, performance issues, data management issues are just gone.
Yeah.
How would the world change?
So this was really surprising to me, to just give an anecdote to describe to people who don't understand what you're saying here, which I think is a lot of people. I think a large number of people. When you're just yourself modeling in home in Fusion 360, you've got a couple parts maybe in an assembly. It's not that big of a deal. Even in SMB or small to medium sized business, your assemblies aren't that complex.
Yeah.
Right? But the second you go into enterprise or you're doing something really complex like a satellite or a car or a phone, there are literally teams of people whose job it is just to manage the assembly. And oftentimes, they're not even the engineers designing the thing.
Yep.
They're literally people in an office who just sit there in front of CAD making sure that it all loads and looks right.
Yep.
This is so surprising.
Yeah. So let's how would the world change if we could load 10 million parts on an average computer, not on a workstation. On an average computer, we could load 10 million parts without any dumbed down representation, like the raw assembly. We could load it in at 20 seconds.
And this is a problem caused by BREPs?
Yes, of course.
So, and by the way, I guess there's the proof in the pudding of why BREPs lack a little bit here, because we had this technology in 1990, and today, 30 years later, despite Moore's law, you still can't really do it. Mm-hmm. And it's just because BREPs just don't compute.
Because of the math. So that's just one issue that BREPs have. Or what if we could run simulations 1,000 times faster, right? What if we would have literally real-time simulation feedback, which is, by the way, this is what physics AI companies are doing, right? And there are some really promising results from physics AI companies, but there's a fundamental bottleneck for implementing physics AI workflows, is that to train a physics AI model, you need these fully robust parametric models that always update and easy to evaluate. Again, you can't do that with BREPs. So if simulations were real time and would be with a single click, I could just turn on simulation mode in my design software, and as I'm extruding something, I see a real-time feedback on my large assembly, how the physical properties of my designs are changing. Or if I can use AI to engineer something for me because it has the right tools. Again, how would that change what's possible to build?
Weirdly, the FEA and simulation angle, I think, is not very valuable, believe it or not. Despite creating an FEA company, I actually don't think FEA is very valuable to engineers.
It's weird.
It is weird, but it's not. I won't get into it necessarily, but all I will say is engineers want to do FEA, but the problem is our day is so burdened by everything else, like managing drawings and arguing with vendors and all of that stuff. In a perfect world, we would do FEA, but we don't.
Yeah.
You go to school to do FEA, and then that's.
Yeah, I don't disagree with that. It's just that. So look, I think. But I think just like every other tool, FEA can be used well, and FEA can be used poorly. And I agree that a lot of people are just using FEA to create pretty pictures, right? And to make.
Do you know what CFD stands for?
Yes, I know. Yes, I know.
Colors for directors.
Yeah. So yeah, I don't disagree with that. I'm just saying that I think if solving the geometry problem would probably unlock previously impossible workflows that could completely transform what is possible to manufacture. That's what I'm saying. So and I think that's and it doesn't mean that BREPs are limiting for the current workflows, because the current workflows are built for BREPs, right? It's a bit of a
chicken and the egg.
Yeah, exactly. So yes, but we have what we have because we have BREPs. But if we solved all those problems that BREPs cannot solve today, that would probably have a global GDP level impact without exaggeration. So in that sense, yes, they are limiting.
You are in a way. Well, actually, let me ask. Do you think that the bottleneck on that 16% not being 25% is human time capital and IQ and brain power? In other words, if it were 50% easier to do the work of a mechanical engineer in the software, you would see that unlock that you're talking about?
I mean, it's not. I'm not sure if it's the right way to think about it. That we would indeed increase that 16% to 25%, or we would just it would just remain 16%, but we would produce much better products, right? And the GDP impact would not it would not increase the GDP, but at the same cost, we would build much better products, right? So, because again, the ratio of manufacturing GDP is not necessarily the right number to look at, maybe absolute number increase or something like that. But yes, I mean, I think it's definitely possible. Look, you've worked at very large manufacturing companies before, right? So you know exactly how many inefficiencies there are, how many people are doing things that probably don't require that many people, simply because of the bureaucracy and administration and all the overhead, or simply because how limiting the tools are, because you wait for your CAD system half a day to open your large assembly, right? And so I think there are probably a 1,000 different ways how you can get there. I think a part of it is just simply unlocking previously impossible workflows, from physics AI to large-scale metal 3D printing finally becoming a reality, right? And then there's another aspect, which is simply just improving the time efficiency of engineers and making them faster by providing them better tools. So I think technological shifts play out in unexpected ways usually, right?
Why was there a split between the ID surfacing tools like Elias and the actual engineering tools like NX?
Because they solve a different problem. It's one is more programming, that's engineering, and that's what SolidWorks is doing and NX is doing and what parametric tools are doing. And the other one is more sculpting. That's why. But one is art, the other is programming.
But they end up being BREPs anyways. So
yes.
Why weren't they co-opted? Why?
For the same reason you have accounting software where you enter text, and you have Microsoft Word where you also enter text, and both are text. So it's a different workflow. Yes, both end up being BREPs, but BREP is just math, right? And then the shapes and forms you want to represent with a BREP are completely different when you're engineering and when you're sculpting. And those require different tool sets. But it doesn't mean that mechanical CAD tools are not used for producing artistic surfaces. CATIA is famously good at creating Class A surfaces in automotive industry.
Right? NX has it. There's a march towards this trend. Yes. I think of even SolidWorks now has decent surfacing.
Yes.
So, I wanted to ask this earlier, and I think it's probably relevant now. But why we were talking about, you have these specialized tools you have these generalized tools, I should say, like SolidWorks, where engineers, I think you said 40 or 60% of the medium-sized market is SolidWorks. It's half.
Yeah.
Why didn't NX or CATIA, one of these super high-end tools, say, actually, we're going to go after that market too, and just release a slightly dumbed-down version and go after that market? And
I don't know. You should ask their management probably. I think this is not CAD specific, not engineering software specific. Enterprise companies rarely move down market. Rarely. I can't really think of any successful examples, to be honest. Moving up market happens more frequently than moving down market. And then those companies that started as an SMB mid-market company and moving up market, those very often keep their mid-market share and then become successful in enterprise as well. But even that move is actually brutally hard because it comes with a cultural shift and a go-to-market shift. It needs different marketing, sales, different positioning, messaging, everything. It's like selling like a carrot to an enterprise company and to a mid-market company. It's a different process. In enterprise, you need like multi-level messaging from the individual contributor to the C-level and everyone in between, and then you have a sales process with 10, 15 different stakeholders, purchasing committees, buying committees. And in a mid-market company, often you have Joe, who is going to be the buyer, and then you hang out with Joe and you are market to Joe, but Joe is not going to give you $1 million. Joe is going to give you $50,000. Because of that, the way you build your go-to-market engine is just very different, and it has to be much more efficient. So these are different beasts.
So they were already catching whales. They didn't want to go catch fish.
Yeah.
So what's more difficult, building a geometric
and maybe one more thing, like if, actually Dassault does this with SolidWorks. Like SolidWorks is owned by Dassault, and Dassault owns their mid-market share with CATIA, and they own the enterprise market, own their enterprise market share with CATIA, and then they own the mid-market with SolidWorks, right? Siemens has Siemens NX, and they also have the little brother of NX, which is Solid Edge, but Solid Edge is not a very successful product. It's like it's relatively small.
Do you think that what is the distinction there for them? Because in my naive take, it would be, well, just combine them in one product, and that simplifies everything. Is the problem that, well, but the engineers designing cars have a very, very specific and more challenging need than engineers designing whatever they're designing with SolidWorks?
It partly comes down to large assembly management and how assemblies are being managed. Like typically the mid-market tools optimize their assembly management for the needs of SMBs. And then enterprise tools have PLM integrations or have like different kind of PLM integrations. The way they manage assemblies is different. Like there are a bunch of like workflows that enterprise companies have that mid-market companies just don't have.
Do you see? So you have a unique position at Shaper 3D where, like in most B2B SaaS or just software development in general, it's just all CRUD apps. It's like Salesforce is literally just a front end with a back end, and they're just moving text around.
Yep.
You, on the other hand, have to do that plus do computationally intensive calculations. You have to hire PhDs and software developers. Do you see a distinction within the company that you actually sort of have different types of software developers?
100%. I mean, that's how Neumann was born. We have a research team, and they were working on some of the hardest problems in our space since 2019, and then they cracked some of those problems, and that's how Neumann came to existence.
So, for those who don't know, you are the founder and CEO of Shaper 3D, and Neumann is a new thing.
And I'm founder and the CEO of Neumann. Yeah. Okay. Yes, Neumann is the new thing that we are going to launch later this year.
So you thought CAD software wasn't hard enough, so I'm going to do it again. I'm going to be a CEO twice.
We will see what it is.
Okay, and you can't say anything yet, so we'll leave it there.
I can't see I can't say what it is, but I can say that it is designed for solving the problems that you can't solve today. And there are many, many problems like that. I talked about this, right? That B reps are great for cubes with holes, and then when you move beyond cubes with holes, they are maybe less great. And there are a lot of complex advanced manufacturing workflows, simulation workflows, CAM workflows that are simply not possible today. And yes, I believe that it could make a GDP level impact if we would unlock those workflows.
Something I noticed the other day, it was someone, I forgot who said this, but it was Peter, now that I remember. He pointed out that if you look at machines and assemblies from the 60s and 70s, they actually were more complex. And if you look at them from the 90s onwards, they actually got less complex in a way. Like a toaster from 1960 is way more difficult to model than one today, believe it or not, in terms of if you open it up and look at the geometry and everything. And so it's almost like we've seen a regression in what engineers are capable of doing. And it probably is because of the technology stack that we currently have.
I don't think so.
Really?
I mean, look at the Raptor engine, famously.
Yeah, but look at Voyager 1 and 2 and all of the engines that NASA could have developed. It was just as...
I think there is no correlation. Like simplicity in geometry doesn't mean less advanced engineering. I think it's more advanced engineering. I would not benchmark the sophistication of engineering with the complexity of the geometry.
Fair. Yeah, so the Raptor engine it's way fewer parts, but it took way more engineering and complex engineering to get it to be simpler.
Yeah.
I agree with that.
That's my point.
What I mean is, if you look at the actual geometries themselves, I think that there was a regression. My favorite example of this is if you look at like a toaster from 1960 versus a toaster today, it's like a caveman designed the one today and a genius designed the one from 1960. I implore everyone to go look this up. It's actually very...
But okay, and how much did that toaster cost at the time and how much does it cost today?
Fair.
And how many people did we lift out from poverty by making things better, faster, cheaper,
yes,
right?
Yeah.
So I think yes, of course, like you can. I would be very cautious with this, like with the fallacy of like everything was better at the time, right? Because I think it's really easy to look back things and they were different indeed, but we ended up where we ended up for a reason, and it looks like that people have more and better stuff today than what they had, I don't know, like 50 years ago. So like we can deeply appreciate the engineering of the 1960s and 70s, toaster engineering, but we can at the same time we should also admit that more people have toasters today, and that's largely thanks to engineering.
That might be because of capitalism, not because
hell
of...
yeah. Let's go.
Is software development engineering? Are software engineers engineers?
Oh, we are getting into the Twitter question.
Yeah,
right?
yeah.
Like, of course. Yeah. What's
Your
next?
answer could be no comment, by the way.
Oh, yeah. So, I mean, in a way it is. It's but I mean, I totally understand why some people are triggered by that expression. And I think just like in every profession, there's like a spectrum of software engineers as well. And I would say that yes, the more advanced, more sophisticated, or the most sophisticated software developers, I think they are doing engineering-like job in a way. They design things, they measure them, they test them with an engineering mindset. But I wouldn't say that every software developer works like that, and I wouldn't say that every software developer has the engineering mindset. But I think actually the best software engineers tend to be actual engineers, and they have engineering mindset. And very often, actually, there's an overlap between between mechanical engineers and the best software engineers in my experience.
One of the going back to the question before this one, what I was most surprised by at Shaper was your best software engineers happen to be physicists, or
Yeah, I wouldn't say the best, but we have a bunch of really, really, really smart folks who are mathematicians and physicists and mechanical engineers, and then they pivoted to software. And yes, they tend to be quite successful at Shaper. It's interesting that, and also at Neumann, actually in the Neumann founding team, we have a lot of multidisciplinary people who have strange backgrounds, like unusual backgrounds.
what's the strangest?
The strangest. They're maybe not strange. Maybe strange is not the right word, but like unusual, like not
Atypical,
software engineering backgrounds.
Yeah.
Not Michelin star chefs or like,
So what about you? What did you get your degree in? Did you get your degree?
I'm a software engineer, if I can say that.
But you have a physics degree, so I think
I don't know. I've wrote my master's thesis about numerical simulations, running quantum mechanical simulations on the GPU, which was at the time, not like I'm that old, of course, but at the time it was quite novel.
Was CUDA around at the time?
Yeah, not even OpenCL actually. OpenCL just came out. At the
Okay.
time. Yeah, so that was really interesting. I wanted to do a PhD actually, and then I realized that it's not for me. Like I like building stuff that people actually use and not just like writing papers and publishing them.
So you got your bachelor's degree in software engineering or computer science,
Yes,
and you went and got your master's in computer science as well.
correct.
Okay.
Yeah.
And then did you start the PhD? And then
I did not. I was deeply uninspired after I visited the PhD school, and I looked around and I was like, no, this is not for me. So, yeah.
you did that here in Budapest.
Yeah.
How did you get into computer science as your?
It was inevitable. I started coding very early. I started coding when I was 6, actually. So my brother is an architect, and but he wanted to be a software engineer, and he's 10 years older than I am. And when he wanted to be a software engineer, he basically taught me how to code. He had a Commodore 64 at home, and I was writing basic code on the Commodore 64. It was pretty cool.
There was no internet at the time. Or
There was. Actually, we were one of the first. Like, we had internet at home in 1994. It was quite early.
But could you actually use it to go figure out how to write programs?
At 1993, actually. Sorry.
Wow.
Wow.
But how did you learn? Was there just a great instruction manual that you had, or?
No, I had we had a book, like programming for children on Commodore 64, and and I just read it, and I was typing in the code from the book, and I was modifying it, and that's how I learned it.
Do you remember any of the games you made, or anything you wrote?
Made games. Not really. I mean, when I was young, I built like very basic stuff. Like I was just learning like what a for loop is and what a if statement is. So it was very like it is really basics. Like maybe like a 100 lines of code. The most complex cases. I was not writing games when I was 6 years old. I just like started learning how to code. But I got quite obsessed with it. So it remained a hobby. And then and then from my pocket money, from my savings, when I was, I think 11 years old, I bought Bjarne Strostrup's C++ programming book.
Wait, how old were you at the time?
At 11. And this was that's like 2 books like this thick. It's like in total like 1,500 pages. And I actually read it. And my mom still like every time when this comes up, he still tells everyone like, and he bought the book and he actually read it, all the 1,500 pages, like all of it. And actually I did read it. And then I learned C++ when I was like 11, 12 years old. And then I got into coding like more seriously. And then it was quite basically, and then I learned, and then my brother became an architect. So when he was studying on the university, I was sitting next to him on the weekends and I was watching him using AutoCAD and 3ds Max. And I learned 3D modeling from him. So I guess it was inevitable for me to build a CAD company or three.
Wait. So what was, I know Shaper 3D and now Neumann, but what was the first one?
So I had another one 15 years ago, before, like 5 years before Shaper, which failed. It was basically a visual programming language and like a node-based visual, like you know Grasshopper, right?
Yeah.
It was a bit similar to what Grasshopper is, but we try to make it work in both directions. So it's not just that you could create geometry from nodes, but we also try to make the other way around, like creating the code from modeling workflow and making it work for both directions.
And did you do that full time as a startup, or was
No. We raised some money and then we went bankrupt. Yeah.
How long did it go for?
So I was with the company for 2 years, and then I left. My co-founder stayed for 1 more year, and then they went bankrupt.
How did you explain to your wife when you started Shaper 3D? Hey, remember that idea that I had that failed? I'd like to do that again.
I did not. So I mean, I didn't have to. Like, no. I mean, that's not like. And I was like, basically it was a completely different bet, right? A completely different idea. So, CAD, but not the same.
How did you get the idea for Shaper 3D instead of what you did before?
Yeah. So, you know that Shaper started from the iPad, actually.
Right.
So now Shaper is available on Mac, Windows, Vision Pro, and iPad, but originally it was an iPad app. And the founding thesis of the company at the time was that the iPad was new, the iPad Pro was new. And basically the founding thesis was that if Apple was going to do the same with the iPad that they did with the Mac in the 1980s, that they are completely changing the personal computing industry, then this might be the beginning of a platform shift. And then if you reinvent CAD from scratch for iPad, then we can just ride the wave of that platform shift. This is like 2016, keep in mind. So at the time, this was a reasonable assumption. And of course, that platform shift did not happen, right? So like the iPad is moderately successful. And then in 2020, we also realized that, okay, the iPad is not going to take over the world. So we should explore different directions. And then that's when we added support for Mac and Windows, and we started scaling, and then we moved up market, and then we basically used this like hobbyist user base to serve as a lead generation engine for enterprise. And then from that user base, we started to get more and more interest from enterprise companies, and then we pivoted, maybe not pivoted, but added enterprise support as well.
So knowing what you know now, what advice would you give yourself either when you started Shaper or the first CAD company, based on what you know now?
Don't do it. No, I wouldn't say that. Actually, I would. What advice? To be honest, I'm not sure, to be honest, because I think like it's always easy to be smart retrospectively, right? How does it matter? It's like this is like, I don't really like these what ifs, because I would say that at the time, based on the context that I had at the time, I think most of the decisions were not fundamentally wrong that I made. But I just didn't have enough context, and I didn't know enough. And it's like, I learned a lot since then. But I don't have too many regrets, to be honest. I would probably do a better job with how I raise money, how I work with my investors. I would probably do a better job with hiring. I would make less mistakes. I would, so probably I wouldn't, I would probably do almost everything differently today, but it doesn't mean that at the time any of those decisions were completely wrong or I feel like really bad about them. I think based on what I knew at the time, those were relatively good decisions.
So it would have been something like pay more attention to this or do this slightly differently when it comes to raising?
This is again like probably I could tell myself like if somehow I could transfer all these experiences that I went through in the last 10 years, that would be obviously useful, but it's not a single thing. It's like just like entrepreneurship transforms you. It turns you into a completely different person. You learn, you fail, you learn, you fail, you learn, you fail, you learn, you fail, and then eventually you succeed. Yeah, and that's okay.
All right. Well, István, thank you for creating one of my favorite applications.
You're welcome. Thanks for being a user.
I'm looking forward to the next thing.
So am I. Appreciate it. Thanks for
thank
having
you.
me.